All right, so here we are with lesson 1.3, radian measures. So this could be a very new topic for some of you, especially if you've never taken pre-calc before. So a couple of definitions here to get started and visualize some of this vocabulary. So a central angle is pictured here, right? So that's any angle that we're talking about, all right, that rotates around the circle. Okay, that's called the central angle. All right. And then the intercepted arc would be whatever the arc is that is intercepted by that central angle. So this intercepted arc will be right here. Okay. Now in geometry you talked about major arcs and minor arcs, and typically an arc is going to be labeled with multiple letters. So let's just say this is D. We had another letter over here, O, and then we had this point here as being G. So major arc DOG, right, would be the larger arc. Minor arc DG would be the smaller arc. So just some other things that you could see as well. A radian, 1 radian is the measure of a central angle of a circle that intercepts an arc equal in length to the radius. So it's almost like a equilateral triangle, okay, in that side equals this side. Okay, so it's not a triangle because this here is an arc, not a side. Now something to keep in mind here is circumference, okay, and that's where radian measure is derived from. So an entire circle has 2 pi radians, okay, so you're seeing that listed here, 2 pi radians for an entire circle, which is the same as 360 degrees, but the conversion that we're going to end up using is pi radians equals 180 because it's smaller numbers to work with. So first, let's convert radians to degrees, degrees to radians, find the measure of the angles below. What's the radian measure for a 60-degree angle? So if you're using a proportion, which is not my preferred way, all right, but I will teach you both ways, the proportion that we're going to use, and the nice thing about the proportion is the same every time. We're going to use D over 180 equals R over pi. Again, we're comparing like items, okay? So D for degrees, R for radians. So I know 60 is a degree measure, so I plug that in for the D, so 60 over 180, and that's going to equal R over pi. And now I'm solving for R. All right, typically when we're converting to radians, we're looking for a reduced fraction, which means we want to have pi in our answer. So I'm going to cross multiply 60 times pi and 180 times R. And then when I solve for R, I'm going to be dividing by 180. And when I reduce this fraction to find my radian measure, I do not want to touch the pi. I just want to reduce the 60 over 180. And I'm going to find out that that equals 1/3. So pi over 3 would be the radian measure that's equivalent to 60 degrees. Slide over to the next one. Convert 85 to radians. Again, I'm going to start with the proportion. All right, D over 180 equals R over pi. I'm going to plug in for D, which is 85 degrees over 180. And that equals R over pi. All right, I'm going to cross multiply. Notice how the process basically repeats itself. 85 pi equals 180 R. When I divide by 180, again, I'm only reducing the 85 and the 180. And when I do that, I'm going to end up getting 17 pi over 36 equals my radian measure. Again, I don't want decimals here, right? I want a reduced fraction with pi in it. Last, convert 2.5 radians to degrees. This one's a little bit different here. All right, we're given a radian measure, so still using the proportion, D over 180 equals R over pi, except now I'm substituting for R. So D over 180 equals 2.5 over pi. Okay. And if I'm converting to degrees, decimals are okay. Right? So I can just cross multiply this. Okay. D pi equals 180 times 2.5. And then divide by pi. And when I type all that into my calculator at the same time, my degree measure comes out to be 143.2 degrees. All right. Now, if I'm using dimensional analysis, this is my preferred method, and it cuts a step or two sometimes out. If I'm converting from radians to from degrees to radians, I'm going to multiply by pi over 180. Again, I'm trying to put pi in the answer, so that's why pi is going to be on top. I'm trying to reduce the degrees, which is the 180, so that's why degrees goes in the bottom. If I'm going radians to degrees, then I'm going to multiply by 180 over pi. Again, I'm trying to put degrees into the answer, and I'm trying to cancel the radians. That's why the pi is in the bottom. All right, so if I use dimensional analysis, pi over 2 radians, I don't want radians, I want degrees, so I got to multiply. I need my degree to be on top. I want my pi to cancel. So pi over 2 times 180 over pi. Okay, notice how pi's cancel, and I get 180 divided by 2, which is 90 degrees. Okay, but if I have 225, right, now I have degrees and I want radians. So 225 degrees times pi over 180. Again, pi is going to be in my answer, so I do not want to multiply anything here. I want to just simply reduce my 225 and my 180. Okay, and they will reduce to 5 pi over 4. If reducing 225 over 180 in your head is a struggle, okay, then you could always use your calculator and then just change it back to an improper fraction. All right, but in this case, it would be divisible by 45. All right, 2 radians, but I want degrees. All right, so times by 180 over pi. And anytime I want degrees, decimals are okay. So I literally can just type it in, multiply these on the calculator. I get 114.6 degrees. All right, and then last 150. Again, 150 degrees, but I want radians, so I'm going to multiply by pi over 180. I want radians in my answer, that's why the pi goes on top. I'm trying to cancel degrees, that's why degrees goes in the bottom. All right, and when I do that, I'll get 5 pi over 6. Okay. All right. Cosine sine of radian measures. Again, this is still using the unit circle. All right, so we're still locating these places on the unit circle. Notice, all right, if I go to my unit circle, all right, that was handed out. Each of those degree measures is also paired with a radian measure. Okay, every single one of them has a degree measure and a radian measure. So we're still at the stage where we're doing search and find. Okay. So if I'm doing this question here, cosine of pi over 4, I'm finding pi over 4, and cosine tells me x value. All right, so that's going to be a root 2 over 2. Sine of pi over 3, that's first quadrant, and sine tells me y value. So again, if I look for pi over 3, it's going to be this one right here in the first quadrant, and I want the y value of that, which in this case is going to be a root 3 over 2. And you should be looking at your unit circle for these. All right, and then we have arc length. Okay, now that we're talking about radians and circumference, we can also talk about arc length with that. And if your degree or your angle measure is in radians, the equation for arc length is super simple. You just multiply by the radius. Okay, if it's not in radians, then you would convert to radians first and then find your arc length. And you're going to find some other shortcuts along the way. So example 4, use a circle to the right, find the length s to the nearest tenth. All right, so arc length S, we're going to assume is this arc length right here. So if I know that my angle is 5 pi over 6, and I know my radius is 3, I'm simply going to multiply the two of those together to find my arc length. All right, so I end up getting an arc length of 5 pi over 2. Okay, and you can very simply, if you're looking for a decimal answer, like this is some sort of measurement that we need to have, you know, an approximation, then I would just type that in the calculator. And in this case, I would get 7.9 inches. What about arc length B? Okay, well, arc length B is going to be very similar to A, except now my angle is actually 2 pi over 3. So theta is going to be 2 pi over 3. Okay, the radius is 3, so arc length is going to be 2 pi over 3 times the radius, So my 3's end up canceling, and I get arc length of 2 pi, which in this case, if I need a decimal answer, that would be 6.3 inches. All right. And last, use the graph to find the intercepted arcs. Oh, there's one more after this. Okay, so again, we can label as much as we want about this. Okay, like if this, in other words, if this part of the angle is pi over 4, that would mean that this part has to be pi over 4, right? Because that's 45, 45. All right, if this one's pi over 3, okay, then this right here would have to be pi over 6. Because together they'd have to add up to be half a pi, pi over 2. So if I start looking for some of these, AOB is pi over 4. Right, here's AOB. Okay, this one's AOB right here. And then let's see here, COD. COD would be this one right here that's given to us as well. It looks like that one's going to be pi over 3. All right, AOC. Okay, AOC is this angle right here. AOC, so that's a 90. So pi over 2. And finally, we have AOD. So AOD. Okay, so I have the pi over 2 from here plus another pi over 3. All right, and I believe that's going to end up being 5 pi over 6. And you could add those together. So I would do pi over 2 plus pi over 3. And that gives me 5 pi over 6. Real world problem here. So whether satellite in a circular orbit around the Earth completes orbit once every 2 hours. Radius of the Earth is 64 kilometers. The satellite orbit is 26 kilometers above Earth's surface. How far does the satellite travel in 1 hour? Okay. So the radius, if we think about what our diagram looks like here, right? Not only do we have the Earth, which has the radius of 6,400, okay, that we know about, okay, and then we have the satellite orbiting above Earth, okay. So the satellite is orbiting above Earth, all right, which is another 2,600 kilometers. Okay, so that means our total radius here ends up being 9,000 kilometers. Okay, our angle is 2 pi radians because it says that it takes the whole way around. Okay, which would be 2 pi for 1 orbit. And our formula here for arc length equals r times theta. So I'm going to have 9,000 times 2 pi. Okay. So that's how far it's going to travel in 2 hours, right? Because it makes 1 orbit every 2 hours. Okay. So if we want to find out how much it travels in 1 hour, let's actually calculate this first. So my arc length for 2 hours, 1 whole orbit or 1 circumference around is, looks like 56,548. If I type that in my calculator, 9,000 times 2 pi, 0.67 kilometers. And if I want to know 1 hour, then I'm going to divide that by 2. Right? We're assuming it maintains the same speed throughout the orbit, which means the satellite travels 28,274 kilometers per hour. Seems really fast. But again, that's relative to a person standing on Earth. Okay. All right.